This conference will now be recorded.
So, good evening. Today we'll be discussing about Hertz experiment and the mathematical formulation or mathematical form of electromagnetic wave to understand the electromagnetic wave mathematically in our known wave form, and we'll learn few concepts about electromagnetic wave which will be useful for solving various numerical problems. In fact, we'll take up few numerical problems also in this class. And then we'll conclude this chapter. The remaining part is the electromagnetic spectrum. So those are very trivial things. If a student reads, maybe things will be clear to him. So we'll not go much detail on that part. So today will be the concluding lecture on this electromagnetic wave. Okay, so let us start with our discussion about Hertz experiment first. So you might be thinking, what is so important about this Hertz experiment? Look here, we have already learned that Maxwell actually predicted about the existence of EM wave, electromagnetic wave. Okay, but it took, so this was a prediction from his mathematical rigorous theoretical calculations and derivations from Maxwell's four equations, which we have already discussed in the last class. So he had formulated a theoretical equations which was very similar to a wave equation, and from there he predicted that there is a wave called electromagnetic wave, which is a combination of electric and magnetic field, and in the vacuum the speed of that EM wave is equal to c. So that's how electromagnetic light is electromagnetic wave, that was proved. So far that was very good, prediction was very nice. But in physics or in science, anything which cannot be proved experimentally or observed the effect of that particular theory experimentally, so that cannot be established as a theory. So that can be a prediction or hypothesis until and unless that is established by experimental evidences. So Hertz was the first person. He was a German physicist, Hendrik Hertz. He had performed a very simple and primitive experiment on this fact, whether the existence of electromagnetic wave can be proved experimentally. In fact, many scientists in many labs, it was like experiments were going on, but Hertz experiment successfully could explain, and it was actually after the prediction 20 almost 22 years passed 22 years passed after the prediction to happen to 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 be proved this fact. Okay, so anyway, today we'll just discuss the Hertz experiment. Actually, there there will be two outcome or two conclusion from this Hertz experiment. One is that existence of elect existence of EM wave, okay, and during the time of this prediction, only longitudinal wave was known. Sorry, both longitudinal and transverse waves were known, but there was an idea that wave means there there should be a medium through which a wave can propagate. But this Hertz experiment proved that EM wave does not require this property of electromagnetic wave we have already studied. But see, the Hertz experiment first proved that electromagnetic wave does not require does not require a medium to propagate. Okay, so these two facts were nicely established or proved from Hertz experiment. Let us discuss the experiment and then we'll see these conclusions whether these are met or not. Okay, so this is the figure, simple diagram of the experimental arrangement. I'll explain what it is. So you can see this is a coil. This is actually inductor coil. Okay, there is a capacitor over here, and these are two metallic sphere. If I simplify this figure and draw, there are two metallic sphere with a gap. Okay, these are metallic sphere. Metallic sphere. Okay, now they are connected to a battery through a capacitor. This is one capacitor, and this is an inductor coil. Okay, and through them, these two metallic spheres are connected to a battery. Okay, this is the arrangement over here. So I'll explain what are the roles of this inductor coil and capacitor, etc. Okay, so there is a switch also over here. So there is a switch, and switch has an important role in this experiment. We'll see that. So this is the switch. Okay, so which is shown over here. Look, so in this case, what happens? There is a battery having sufficient power to draw, like flow a current through this circuit. See, when this switch is closed, so there will be a current flowing through this, and there is a gap over here. This is a gap. So in so there will be no current through the this circuit. So no current through the capacitor initially. Okay, initially means when the switch is closed, so battery will flow a current through the inductor coil alone. Now inductor means, you know, when there is a constant current flowing through that, does not matter much. But when there is a change in the current, sudden change in the current, so inductor coil will give a will produce an EMF, that is called back EMF. And you might remember from the induction part, we know this is L di dt. That EMF will be L di dt. Okay. If there is a change in the current, if the steady current is flowing, then induced EMF will not be there across the inductor coil. But when there is a sudden change in the current, then there will be an EMF induced across the inductor coil. Okay. If your number of turns are very large, then this also will be very large. Okay. If this is large, and also if the time interval is very this denominator, if you can make it very small, very small, okay, small, then automatically that ratio will be very large. So see how you can have this EMF across the inductor with this DC battery. What you have to do, you just close the switch. Initially there would be a flow of steady current, then suddenly you have to switch off. Okay, switch off this circuit. Okay, open the circuit suddenly. You have to do it suddenly, so that this is this delta t, if this is in a fraction of second, sorry, fraction of, yes, fraction of second, if you can do, then you can see this ratio di by dt will be a large number. And this large number, if you multiply with this another large number, then it will be a huge number, this as a whole. So induced EMF will be very large. So you can see there are large, this is called high tension inductor coil, high tension inductor coil, because there are thousands of turns, as well as the time interval for switching this circuit off has been taken as very small. So this is a high tension coil which will induce a very high EMF, very large EMF, and that EMF will actually charge this metal sphere. Okay, so this EMF across, now across this gap. Okay, I'll just clean this and then I'll draw here. See, I had metallic sphere with a gap, two metallic sphere with a gap. You, we have a capacitor, we have inductor coil like this. Okay, and then it was connected via a switch, okay, to a battery. This switch was suddenly closed, sorry, suddenly opened. So there will be a change in the current, di dt will be there. So L di dt with a minus sign, there will be EMF induced across this inductor coil. So this inductor coil which will send the charge to these two metallic spheres. So they will accommodate, like accumulate charges. Maybe this will accumulate positive charge, this will accumulate negative charges, and there will be a huge potential difference between these two. So potential difference V, okay, V, potential difference, huge potential difference will be created or produced across this gap. Actually this is a gap, air gap. So air molecules are there over here in this region. Now the high tension wire produce such a large induced EMF, such that the EMF, sorry, the voltage drop across here, or I can say in other word, the voltage difference, change in the voltage means there is electric field. Okay, EMF is actually nothing but electric field also. So it has unit volt per meter. So at this gap, about around this gap or across this gap, there will be a huge electric field, and when it crosses of the order of 6 volt, so 10 to the power 6 volt is actually nearly 10 to the power 6 volt is the ionization, like this is called breakdown voltage or breakdown field over here. Okay, so when the electric field across this gap crosses this or becomes larger than 10 to the power 6 volt, then the air molecules over here will be ionized. Ionized means what? There was some hydrogen atom, then that will be hydrogen plus ion, and one electron will be emitted. So positive charges will go here, and negative charges will go here. Sorry, opposite way. Positive charges will come here, negative charges will come here, like that. Okay. So since there is a discharge, this is called electric discharge, and due to that electric discharge, there will be a spark. Okay, there will be a spark of light. Okay, there will be a spark of light. You learn in detail why, due to electric discharge, light is produced. This will learn in in the modern physics part. Okay, so what happens here when immediately you switch off this? What happens? There will be a huge induced EMF across the inductor coil, which will charge these metal spheres. Metal spheres will be producing, upon getting charged, it will produce huge electric field. That is, if that crosses the amount of electric field 10 to the power 6 volt, then what will happen? Then the air in between this sphere, or in the region of this gap, will be ionized. So ionized, okay, and there will be transfer of electrons from here to here, or charges. This is called electric discharge, and due to this electric discharge, what happens? There will be spark. Okay, there will be spark around this gap. Okay, now look what happens. I have another I have another set of spheres like this. Okay, connected with a metallic wire, like this, kind of our earphone or headphone. So these are metal sphere again, metal spheres connected by a single wire, conducting wire. So this is called receiving loop. I will explain why it is. We'll be able to learn why it is receiving coil, it is said. So look, what Hertz observed is that whenever there is a spark around, like about this gap or around this gap, there is a spark here also. So he could see there is a spark over here also, in the, like in the gap of the receiving loop also, there is a electric spark. If the strength of the spark is larger here, the strength of the spark is larger here also. Okay, so that means, you know, whenever there is a spark over here, spark means light, right? There is some kind of light. Okay, so the light is electromagnetic wave, that we know. So whenever there is a spark, the electromagnetic wave is generated over here. Electromagnetic wave is generated over here. You might be thinking, how do you know, sir? We'll even will get some intuitive answer for that from this experiment. Look what happens. There are two metal sphere over here. When there is a spark between the gap, there is a spark over here also. What does this mean? If there is a spark means there is electric discharge. ionization of air molecules. And how is it happening without any energy? There is no battery here, no battery, no battery. Okay, no battery. So there is no source of power which will produce a huge electric field of the order of 10 to the power 6. So then the conclusion is, see, there must be electromagnetic wave produced by this spark. Okay, and this spark will reach over here and produce the electric field across this gap. Okay, so already the idea was known that electromagnetic wave means there will be electric field and magnetic field. Now you can see from this experiment, you can prove that there is electromagnetic wave. Why? Otherwise, if there is a spark over here without giving any power to this gap or any battery without connecting any battery, how can you get a spark over here also in the receiving loop? So there must be electromagnetic field which is moving up to this gap region or up to here, and the electric field, so there will be a charging over here and there will be electric field produced, and that electric field of the electromagnetic wave will actually induce the huge electromagnetic field over here. Okay, sorry, electric field over here. So that's how there is a discharge. Okay, now you might be thinking, sir, you are saying electromagnetic wave. I agree that since there is a spark, there will be huge electric field, and there is no source other than this electromagnetic wave to pass, like go up to here and produce such a high electric field over there. Now the question is, if this is the electromagnetic wave, there must be some arrangement by which you can see the effect of magnetic field also, which is already present in the electromagnetic wave. So scientist Hertz, what he had done, he had later taken a coil over here. He connected a coil over here, so where he could see that so so he had connected later a coil, okay, around the gap, okay, in this gap region, and he could see that there is a induced magnetism over there. So there is magnetic field created over here also. So E and B over here. Okay, magnetic field produced by this electromagnetic wave. Okay, so from there we can understand and we can conclude about the existence of EM wave. So one conclusion is done, because there is a spark and the strength of the spark depends on the strength on the spark over here. So this is called actually sometime emitter circuit. I'll, I'll tell you about emitter circuit, and this is receiver circuit. In our most of the electronic devices, like communication devices we use, there are emitters, sorry, receiver circuit. Okay, now this is existence of EM wave is done. EM wave. Now we'll talk about the second corollary or conclusion. The second thing is that there is no medium or nothing is here, only air or vacuum, you can say. During the time of Maxwell, when the wave theory was known to the scientific community, that time there was an idea that wave is also needed a medium to travel from one place to another. And for electromagnetic wave, especially for light, there is a medium called ether. Okay, there was an idea that there is an ether medium through which light can travel. Okay, but later on, Michelson-Morley experiment of special relativity, they proved that there is nothing called ether medium. Okay, then how can electromagnetic wave pass from here to here in the vacuum? Okay, so people argued that if you say there is wave needs wave needs a medium, but the exception is that Hertz experiment and later on many other experiments established that there is no need for any medium for an electromagnetic wave to travel from one point to another point. Okay, that means for the propagation of electromagnetic wave, no material medium is required. No medium is required. Okay, so these two facts were established from here. So this is very important experiment, and this experiment was done by the same person after whose name the unit of frequency is being given, that is Hertz. Okay, unit of frequency is after his name. Now we'll go to the mathematical form of EM wave. This we had already discussed little bit, but I will discuss again in detail, and then we'll go to few concepts related to the numerical problems. Okay, so let us see electromagnetic wave. It is actually a combination of electric field and magnetic field. Okay, combination of electric and magnetic field. So in general, electromagnetic field is written as E is equal to E0, then sine omega t, sine of omega t minus kx. Okay, I'll sorry, let me just get the figure. Okay, so according to this I'll write. So we have already discussed that electromagnetic wave is a combination of electric field and magnetic field, and we have seen from the properties of the electromagnetic wave that these two will be perpendicular, and propagation vector direction is propagation of the electromagnetic wave. The direction of propagation of electromagnetic wave is actually denoted by k, that is called direction of propagation of electromagnetic wave. So electromagnetic wave, like both electric field and magnetic field, are perpendicular to each other. Electric field and magnetic field, they are perpendicular to each other, and also separately electric field is perpendicular to the propagation vector k, and B is also perpendicular to k. Okay, propagation vector. Okay, so far so good. Now look how to write mathematically electromagnetic field. So you can see here electromagnetic wave. In this particular figure, electric field is oscillating along y direction, sorry, x direction, and magnetic field is actually oscillating along y direction, and electromagnetic whole wave is actually propagating along z direction, z direction. Okay, because they are all mutually perpendicular to each other, that's why this is the thing, that your electric field is oscillating along the b direction, sorry, along the x direction. You can see this has been taken as x here, and magnetic field is oscillating along the b axis, so which is here, sorry, y axis, which is this way, y axis, and this is z axis. Okay, now according to this figure, if I write my electric field has to oscillate along the x-axis direction. So I will write here a ex e0 sine omega t minus kx. Okay. Oh, I'm sorry. This is kz minus kz. So what does this mean? This is actually the peak value of the electric field. This omega is the frequency of oscillation of the wave. Okay, frequency of oscillation of the wave. Okay, oscillation of the wave. What is this k? K is called propagation vector. Propagation vector. Okay, and this vector can be obtained, propagation vector can be obtained by 2 pi by lambda, 2 pi by lambda. Okay, this is propagation vector. Now look, what does this minus kz mean? Minus kz meaning is that the wave is propagating along positive z direction, positive z direction. Okay, what does this minus kz mean? Minus kz meaning is that the electromagnetic wave is propagating along the positive z direction. Okay, similarly I can write the expression for the magnetic field also, and you have to remember that the electromagnetic wave has same frequency for both the fields. Same frequency, so I can write similar way, in similar fashion. This is a y along y direction, so b0 sine omega t minus kz. You might be thinking, sir, you are writing over here by, what is this kz? This is inside the argument of this sign, and this means that the whole wave, you are taking individual component ex ey, but the whole wave by, whole wave by, sorry, not whole wave, this is not whole wave. Whole wave means the combination of electric and magnetic field. So that is the whole wave which will be propagating along the z direction. So that's why this minus kz, omega t minus kz, this argument is same for both of them. Okay. Only thing is this E0 and B0 is making the difference. So what my point is here, that you look, electromagnetic wave is a combination of electric and magnetic field which are oscillating in a particular direction. And if the figure is given, if you have to write down a mathematical form for this electromagnetic wave, you can write in this way. Okay, E you can write separately, B you can write separately. Okay, This is how you have to write. Okay, now this expression itself can be transformed into some other form like C omega by k is equal to C. So this expression can be sometime replaced. Okay. So you can do all sort of things over here, and there will be various form of this argument. Okay. Sometime uh, k z minus omega t also will be given. Kz minus omega t means the, so if it was given like this, the wave is actually propagating in the negative z direction in this case. Okay. Anyway, now will be, so we have already learned about the relation between E0 and B0. Okay. E0, that is the peak value or magnitude of the electric field, is equal to C into B0. So this you know. Now if some expression for the electric field is given, then you can write the expression for the magnetic field, or in vice versa, in the opposite way also you can do. Now let us take one numerical example to understand this fact. So suppose there is an electromagnetic wave, frequency is given as, frequency is given as 20 megahertz. Okay. And suppose at a particular instant of time and a particular space. Okay, so electromagnetic wave is actually propagating along x direction, suppose. So EM wave along x direction. Frequency of the electromagnetic wave is given this much. At a particular instant of time and a particular space, suppose the electric field is this. This is the electric field, that is volt per meter. So you have been asked to calculate what is the B and which direction it is. So vector means you have to find out the magnitude and direction as well. So how to find out that? Okay, so this is the question. See, this can be directly, see, magnitude can be directly found out using this formula. So B0 we will be able to find out. That means the peak value of that. Okay, so anyway, we can find out this by writing E by C, whatever given. So E is given, this is the peak value, 6.3 divided by C is 3 into 10 to the power 8 meter per second. So if you just put these things, this is actually volt per meter. So you'll be able to find out the value for this. So you'll get somewhat like 2.18 into 10 to the power minus 8 Tesla. Okay, so this will be B0. Now I have got the magnitude of the electric field, sorry, magnetic field, but how to find out the direction of this? Okay, I have got 2.18 into 10 to the power minus 8 Tesla. Now what is the direction over here? So to find out the direction, look, you have to remember one good thing, that the direction of propagation of wave is obtained from the cross product of E cross B. Just remember this, E cross B is directly proportional to the direction of propagation vector. Okay, E cross B. Now I have got that your EM wave has a propagation vector along I cap direction. Okay, I cap direction. That means K is given along I cap. Then what is the direction of this B? Okay, I'll just clean it maybe. CE was given 6.3 3 J cap volt per meter. We have found out B0 is equal to 2.18 into 10 to the power minus 8. Sorry, this is Tesla. Magnetic field is Tesla. So it is Tesla. But what is the direction, like I cap, J cap, K cap? Which direction it will be oscillating? I have already EM wave has propagation vector K. Propagation vector K is along I cap direction. Okay, so we'll be doing this E cross B. Okay, such that we get I cap. Okay, so we know cyclic rule I J K cross product. So I cross J will give you K, and J cross K, that means J cap cross K cap will give you I cap. Okay, this will give you I cap. That means your electric field along J cap, and this must be along K cap. That means along the Z direction. So it has to be along K cap direction. Okay, so you get the magnetic field. So this is how you have to use the properties, and you have to find out the electromagnetic. Like if one of them is given, the other one you'll be able to find out. And if suppose there is an expression given sometime, you might be able to find out various parameters, like what is the propagation vector, what is the wavelength, and what is the frequency, etc. That you have to find out. Suppose there is an example. Suppose By is given 2 into 10 to the power 7 sine of 0.5 into 10 to the power 3x plus 1.5 into 10 to the power 11 into t. So this, you can see that this is k into x. So this is k into x, and this is omega into t. That means this wave is actually propagating along negative x direction. Okay. So this is k and this is x. So you can find out easily what is k. And you have been asked to find out the wavelength of the wave. How can you find out wavelength? We know propagation constant can be written as 2 pi by lambda. So from here you can easily find out what is lambda, 2 pi by k. Okay, if you put the value this, you will be able to find out this. So in this way you can find out what is propagation vector or propagation constant. Okay, other things are trivial. All right, now we'll just learn few things, like say what is intensity of EM wave, and then we'll learn what is the momentum transferred by an electromagnetic wave when it is incident when it is falling upon any surface. Okay, so look, suppose this there is an electromagnetic wave which is crossing this cylinder having cross sectional area A. Suppose the cross sectional area is A, okay, and electromagnetic wave having velocity, this is suppose in vacuum, the velocity has c, electromagnetic wave has velocity of light in vacuum, that is c. Suppose the electromagnetic wave takes delta t time to cross this cylinder or cylindrical region. So what is the length of this cylinder? This is c into delta t. This is c into delta t. Okay, so length is the c into delta t. Now what is the volume of this cylindrical region? I can find out area in cross sectional area A into this. So this will give you the volume of this cylinder. So you might be thinking why I'm writing this volume etc. for this cylinder or cylindrical space, because I need it. So intensity of the wave is defined as the average energy. Intensity of the EM wave is defined as average energy, okay, average energy, EM energy of the electromagnetic wave divided by area into time. So this, so area into time. So what is the average area? So this is the formula we'll get eventually. So to derive this, we have to, what we have to do is we have to get the total energy confined in this cylinder is that the average area into, so total energy if you want to find out which is confined in this cylinder will be average energy. I'll write E average of the electromagnetic wave into the volume, this volume, okay. This will give you the total energy in this, like confined in this cylindrical space, okay. Now intensity of the wave is given by this formula. So if we write that, let us see how we get, what is the expression we get. So I average energy will write actually, okay, so let us see average energy, suppose this total energy, suppose E, sorry, U, capital U, total energy, and this is average energy. U, E average is actually denoted by small u into V. Okay, so sorry, this is average energy means small u. All right. So intensity, in the definition of the intensity of the electromagnetic wave is u and divided by area into time. Area this and time is delta t. Okay. Okay, so just a clarification, small clarification. This is not the average energy here in the numerator. It is the total energy confined in this. So this is total energy. Total energy of the electromagnetic wave which is confined in this cylinder. So this is a total energy. So total energy will be given as average energy into the volume. Okay. So total energy confined in this, maybe I'll write the sentence itself. So this is average energy U into the volume. So this is given by the total energy. So total energy, total EM energy, electromagnetic energy, okay, confined in the cylinder. Cylinder. Okay. So which we can, and divided by area into time. This will give you the intensity of the electromagnetic wave. Actually, this is very, very important. I'll just clean everything and I'll write the definition. So U, total energy, divided by area into time. So this means average average energy into volume divided by, this is volume and this is average energy. So area is A for this. C is the velocity, it takes time delta t. So what will be the length? C into delta t. So which will give you the volume. Okay. And here, so delta t is the time over here. So look here, U into volume is C delta t into area. Is the length into area, and in the denominator also you have A into delta t. So you get U into C. That means if you know the average energy, look what you get. Intensity of the electromagnetic wave is equal to the average energy into the speed of the light. So intensity means average energy into speed of light. If you know these two informations, then you can find out the intensity of the light. Okay. So average energy you can write, see, average energy you can write in terms of electromagnetic energy, electric energy, electrostatic half epsilon naught E square, E naught square into C, or you can write in terms of magnetic energy also, that is V naught square C by 2 mu 0. Okay, in this way also you can write. Okay, so even you can write these forms in terms of RMS also. I'll write this. So mm, you can write in terms of RMS C into E RMS square, or C into B RMS square, and there will be epsilon naught over here, and here this will be mu naught. Okay, so this is how you can find out. If you know the RMS value, if you know the speed of the light, then multiply this constants, then you can find out the intensity of the electromagnetic wave. Or in other way also, if intensity is given, you can find out what is the RMS value or the peak value of the electromagnetic wave. Okay, or the strength of the electromagnetic wave you can find out. I'll just discuss one more point, that is the electromagnetic wave actually whenever it is striking a surface. Okay, so we'll learn that electromagnetic wave has particle nature as well. So that we'll learn in the modern physics part. But here you know in terms of wave itself and wave energy itself, that when it comes and hit over here, it transfers some energy as well as momentum. It gives some momentum, transfers some momentum, and then gets reflected. Some part gets reflected, some part will be absorbed, some energy will be absorbed. So if you know how much energy is being absorbed, then the momentum P will be given by U by C. Okay, the average energy. So the total linear momentum delivered to the surface will be given by average energy by speed of the light. Suppose if this is this surface where it is getting reflected or striking, if this is a perfect reflector, then momentum transfer will be actually twice of that. That means momentum comes with p and then get back with again same p but with a minus sign. So the transfer of momentum will be 2p. So 2p means momentum transfer for a perfect reflector, it will be 2u by c. Okay, so this is the thing. And sometime there will be a question, what is the pressure exerted by the EM wave to a surface? So this is momentum u by c, and for a perfect reflector this is 2u by c for perfect reflector. Okay, for a perfect reflector. And if this you want to find out, then pressure P is actually intensity by C. This is the radiation pressure. It is called radiation pressure. If you know the intensity, so this is called radiation pressure. If you know the intensity, then divide with the speed of light in vacuum, then you will get the radiation pressure exerted by an electromagnetic wave to a surface. Okay, so with this I'll stop the discussion, and with this we are concluding this lecture also, this chapter also. Okay, so this is very important. These formulas are very important, like what is the expression for the intensity, what is the expression for, or what is the pressure exerted by radiation to a surface, what is the momentum transfer to any surface. So these are few points which you need to remember for competitive exam as well as solving numerical problems in your board exam as etc. Okay, so thank you for your patience. We'll stop it here. Bye for today. We'll meet again on Wednesday.